Hello, this is Mr. Huff, and I want to go over a few things in engineering. We've had a couple of things go on this week, and I want to kind of just go over some basic principles and kind of talk about some things that you guys need to think about in general and some specifics, even if it's not necessarily your class. So first of all, let's talk about papers. Right here at the top right, please put your name and class period there. I had some group work turned in and names were scattered everywhere. Front, back, top, bottom, middle. So always put your name and class period on every paper you have that you're going to turn in at the very top right. Include your class period. That helps me sort where things go and where you're at. And that's the first thing I want to talk about. So the next thing is when you're working on paper, be sure to organize your work and include sketches. Think about how it looks. Use spacing, visual space to kind of separate your ideas and your activities. Another thing I want to do is encourage you to use data tables when you collect data. And also use IC. No, let's use ink. Ink. Use ink because pencils are hard to read, especially if I'm giving you like crappy construction paper. If you write on with pencil on top of purple, it's really difficult for me to read, so use ink. Also, that's industry standard. When you work in an engineering notebook, you're never going to use ink in the real world. I mean, pencil. You would not use pencil. You always use ink. And if you make a mistake, do not scribble it out, but instead one line through it. At the companies I worked at, you had to mark a line through it and then initial it so they would know who did that. Another tip I have is be sure you answer all the questions. In one of the assignments I gave this week, I only had 4 questions for you to answer, and most people only answered 3. Even though they were working in a group, they only caught 3 of the 4 questions. So make sure you're hitting all those questions. Then on writing levels, we talked about this a little bit in class, but I basically use kind of a real simple 3-level writing score. So 0, you didn't answer it, or you put a single word, it's not a sentence, or it starts with the word because, and that means that I'm going to have to go read the question before I read your answer. Your answers should stand alone without the question next to it. A level 1 is a sentence, but its meaning is unclear or the ideas in it are not correct, but at least you wrote something. A level 2 is you have sentences, you've got the right ideas and vocabulary in place, you're doing some of the things right, but I'm not convinced that you understand what you're talking about, or you're making a claim and you have no evidence to support it. So a level 3, this is what we're shooting for, is it's clear, it's concise, you have claims that include data, so you're supporting what you're saying. That's what I'm looking for. Organize your thoughts a little bit before you start writing. Some of you do this naturally. Some of you are going to have to work at this. All right, let's move on from there. This is some examples from actual student work. So this is a data table. See how easy this is to digest this. The only modification I would make to this is I would put feet next to the word distance. And I appreciate that they spelled the word trial correctly. But that's what I would do. And that way when I'm looking at the data, I'm just seeing the numbers, not that additional lettering, that repetitive feet thing. So just put the unit with the label and you're good to go. And then also notice this answer here. What they did is they gave me a brief summary of the question. And then they said, this is how my flight performed. They compared it to the class. And her own data, or their own data, we'll say. Also, we have a sketch here, so it's real easy for us to look at it and know what lab she's doing. In this case, it was aerospace. They put 2 cups together and made that fly. We'll talk more about that in just a moment. So when you're showing your work for me in this class, we're going to use the guess strategy. What that means is you're going to list everything that's given and any constants that you know, including the units with those. So you can start out with what you already know before you start working the problem. The U stands for unknown, and you're going to include units with this. This is what you're trying to solve for. Sometimes there may be more than one. And then E stands for equation. You're just going to copy the equation that you're going to use. I would prefer that you algebraically rearrange it to solve for the term that you need. So let's say, for instance, that you have the coefficient of drag equation and you're actually solving for the area of the wing. I want you to rearrange that to solve for area. If you do that, flex your algebra skills. That's great. It makes you a more efficient problem solver. If you have trouble with that right now, just show the equation with the unknown where it is as it is. Then we go to substitution. This is where you list what you're putting in the calculator. This could also be, if you haven't rearranged the equation, you plug in the numbers and show your process of getting to your solution. And then S is for the solution, and include units with this. So you want to make sure to put a box around this or underline it or make it stand out from everything else. Notice that we have units listed with the unknown and the solution. I've taught physics and engineering for a few years, and I noticed that a lot of times you guys will start out solving a problem, and by the time you get to the answer, you forgot what you were looking for. You got the right number, but you don't remember the units, and you just kind of guess and throw something weird in there, and it's not correct if you have the wrong units, and it's not correct if you don't include units. Okay. No naked numbers. Another thing is, don't squeeze your work together. Skip lines between problems. Spread it out so it's easy to follow. You're writing for me, not for you. Okay? If you have any questions on that, let me know. All right, we had a design challenge this week, and one of the things I saw that a lot of people struggled with is you did not spend enough time doing the design itself. You didn't spend enough time thinking about what you were going to construct and how you were going to put it together and how it was going to solve the challenge in front of you. So this is a screenshot from, or just a snapshot of my own notebook. I spent about 10 minutes going through this design. I thought about shapes that are stable. I looked at different bridge diagrams. So my Google search went from bridges to diagrams of bridges to forces in bridges, that sort of thing. And I was looking for something that looked easy to construct, that had a lot of tension on the inside. And even if you didn't know about compression and tension, you could have found pictures of things that looked easy to construct pretty quickly. Another thing I thought about was how I was going to lay it out to build it. So I actually taped it all up like this. So whenever I was ready to build it, I just wrapped it up and it made the structure. Then I thought about how I was going to reinforce the ends by having the top spine connected to the lower portions. And I knew that those were going to be in compression when the weight was put down on the bridge, so that I knew that I needed that to make sure that it was going to hold up to being compressed. So those are some of the things I thought about. So let me back up and just apply this in general. Think about the problem you're trying to solve. Think about the different ways you can solve it and some of the things you already know that will help you to a good solution. Think about how you're going to achieve that, like a process of building, and then some of the key parameters you need to pay attention to, like where, in this case, where compression was, where tension was, that sort of thing. So do that ahead of time. That way, when you start your build, you know what you're doing and what you're trying to achieve. A lot of you were just kind of inventing on the fly. You had a rough sketch, but you really hadn't thought about how it was going to go together. This was my build process. So basically I cut out all the pieces that I need. I made it very simple. I only had one measured piece I needed to do, and they all needed to be the same length. I laid it out on the table, and then I got my supplies ready so I could tape it up efficiently. And then this is my final design being tested. These are some other designs from the class. This one was the highest performing student design. And you can kind of look at their diagram and look at what they actually built, and it's pretty close. This one I was impressed by because I see shapes that you would have seen in your Principles of Engineering class. So I'm seeing that these people, this group, thought about what they already knew and were applying that. Also, I want to talk about writing in your own words. So I had another challenge in aerospace. They had to explain how two cups taped together were flying, and we had a lot of different things. One of the things I want you to do is proofread when you write. I'm going to highlight this one. The air is going around the cup as it travels around toward the around. That's what they wrote down on their paper. This was group work. I assume everybody read that and said, that is a beautiful answer. Proofread your work before you turn it in. Sometimes I see this, and this would be a level 1, maybe 2 writing level. You wrote something down. There's some ideas in there. I don't think you know what you're talking about when you write a sentence like this. And then there's some other ones in here. I really like this last one because this one hits on the actual points of how it works. I think the spinning of the cups made the air push it up. And when we talk about a push or a pull, when we talk about that in physics, we're talking about forces. Yes, and spinning has something to do with it. So let's talk about this a little bit. We're going to look at some engineering principles now. What we're looking at with these cups, this is the Magnus force, and that is the definition is the force exerted on a rapidly spinning cylinder or sphere moving through the air or another fluid in a direction at an angle to the axis of the spin. And that's kind of hard to wrap your brain around that definition. It is very, very precise and very, very correct. We see Magnus force in sports, in curve balls and baseball. That's what causes them to curve. And so what we're looking at in the case of this cup is we have the cup spinning this direction. In this case, we're spinning clockwise, and it's moving to the left, so we have the air going to the right. So right here at this intersection of this, the bottom of the cup, the bottom is moving forward and the air is moving backward. Or another way to say that, the bottom of the cup is moving to the left, the wind is going to the right, so we have a net velocity decrease at the surface of the cup. So that causes a higher pressure on the bottom, and that causes a force up. Okay. We can also look at the top, and we can look at the rotation of the cup going to the right. The wind is also going to the right, and that causes a lower pressure, which produces a force up. So these upward forces are counteracting gravity, and that's why the cup is flying. So that's a real quick rundown of how the Magnus force works on the cup wings. And even though you may not have been in that class, you need to be thinking about physics principles that you know about or that you should be able to go out and read about and investigate. All right, thank you guys so much for listening. This is how I'm going to do this instead of trying to talk to everybody at the start of class. Have a great day. That's all.